In this video, I'm going to make some comments and some calculations regarding Phobos and Deimos, moons of Mars, from the point of view of someone observing them on Mars. So we're going to start off with Phobos first, and the observer sees Phobos on the meridian. That would be due south in between the west horizon and east horizon. So on the meridian at midnight, we want to know how much time is going to pass until Phobos is on the meridian again. And I'm not going to do clock time of day, but just how many hours will pass until Phobos is on the meridian again. Phobos has an interesting orbit. It's fast. One orbit every 7.65 hours. I calculated that in a previous video that's posted on YouTube. Mars has one rotation in 24.7 hours. So it's a little difficult to guess the answer, so we're going to need a calculation. Before I get to the calculation, I'm going to show some sketches here that would help us understand what's happening with the motion. So if I just start time equals 0, and Phobos is on the meridian here for this observer. We have an observer, a little stick figure. Right at this point, we have west and east for the horizons, and we're going to advance. I'm just arbitrarily choosing 3 hours. I'm going to let the clock advance by 3 hours, and let's find out where Phobos and the observer are located. Well, 360 degrees, Phobos takes 7.65 hours to complete one orbit. So times that 3 hours. So Phobos has moved around to 141 degrees in its orbit. For Mars, 360 degrees, one rotation every 24.7 hours, times the 3 hours. And Mars is rotated 43.7 degrees. So I represent that here. The observer is now at this location rather than here. And the horizon line is moved a little bit. Phobos is already set in the east, by the way. Phobos is set and is 141 degrees around the circle. So that was just arbitrarily choosing 3 hours. Now I'm going to advance by 12 hours. And let's see where we are in the process. So ignore the calculation over here for a little bit. But after 12 hours, Phobos doing 360 degrees every 7.65 hours times 12 hours, it's gone 565 degrees. It's gone a full circle and more. Well, how much more? Let's subtract the full circle of 360 degrees. Phobos has gone to 205 degrees away from this sort of 0 degree reference line that's at this spot in the orbit. So I've plotted that here. 180 degrees would be down at this position. So we've gone around once and gone 205 degrees. Approximately at this position is the location of Phobos. Where is our observer on Mars? Well, for Mars, 360 degrees, 24.7 hour rotation, multiplied by 12 hours. The observer has advanced by 175 degrees. So it's right down here. It's not quite to 180 yet. And here's the horizon for this local observer. Phobos has passed the meridian. If we could, you have to sort of let these rotations take place in your mind. Mars rotating slowly, and the horizon is rotating slowly as well compared to the stars. But Phobos is moving fast, and Phobos has moved past directly on the meridian. So 12 hours is too far. Well, now let's try doing a calculation. And that calculation, 360 degrees plus, here's the motion of Mars, 14.57 degrees per hour multiplied by the time. That angle will equal the angle that Phobos has moved through, 47.06 degrees per hour multiplied by t. Well, I'll combine like terms with the t's. 360 degrees is 32.49 degrees per hour multiplied by t. I come up with 11.08 hours. Let's see if that makes sense by making a sketch. So if I let the time be 11.08 hours elapsed from our starting position, how much angle has Phobos moved through? It moves 47.06 degrees per hour multiplied by 11.08. It's moved 521.4. If I subtract 360, again, Phobos is completing a lap. It's lapping the observer on Mars. I get 161.4 degrees for its location. How much has Mars rotated in 11.08 hours? It's rotated 161.4 degrees. So here we have the observer, the horizon, and Phobos is on the meridian. It's between west and east. That's our time for Phobos to get back on the meridian. Well, that's one moon. And let's kind of summarize this with and pose a question. Suppose an observer on Mars sees Phobos on the western horizon at midnight. How much time passes? Sorry, a little bit high here. How much time passes until Phobos is on the western horizon again? Well, it's going to be this same number, 11.08 hours. That's going to be sort of the period between common configurations of the observer and the horizon and the moon Phobos. So let's switch to Deimos now. So Deimos has a little different orbit time. Again, this previous video I calculated that for Deimos we've got one orbit every 30.3 hours. Mars is spinning once every 24.7 hours. And again, let's take the meridian configuration. The observer on Mars sees Deimos on the meridian at midnight. We're going to let that be time equals 0. How much time passes until Deimos is on the meridian again? Again, I want to use some sketches to get kind of an understanding of the motion that's taking place here. And we'll start this with maybe a little bit of a calculation. I'll get the sketches later. But the Deimos is moving 11.88 degrees per hour. Mars is rotating at 14.57 degrees per hour. So this time Mars is the faster motion object in terms of degrees per hour. Deimos is moving slower than Phobos. Well, suppose I just pick 12 hours. After 12 hours multiplied by this 11.88, you could pause and check this with your calculator. I came up with 142.6 degrees for the position of Deimos around its orbit. Mars, taking 12 hours times 14.57, Mars would be 174.8 degrees. Mars is ahead. The horizon is moving ahead of the motion of Deimos now. Deimos will set in the west. So 24.7, if I do one rotation of Mars, where is Deimos? Deimos is at 293.4 degrees. And again, I achieved this number, 24.7 times 11.88 degrees per hour. And we get 293.4. Mars is 360. Let's go for another few calculations here. We'll get rid of this piece of paper. For 2 Mars rotations, that's 49.4 hours. Deimos will have moved 586.8 degrees around its orbit. If I subtract 360, it would be 226.8 degrees. Mars has gone 720 degrees after 2 Mars rotations. If we do 3 Mars rotations, and again, 49.4 plus 24.7 would be the time here for 3 Mars rotations multiplied by these angular rates. And Deimos has traveled 80.2 degrees. If I subtract 720 degrees for 2 rotations of Deimos around the planet, 2 revolutions, so Deimos will now be at a position angle of 160 degrees. This will be a little clearer when you see the sketches. For 4 Mars rotations, Deimos has traveled 1,173.7 degrees. Subtract off rotations, 1080. 93.7 is the position angle for Deimos. For 5 Mars rotations, that's 123.5 hours. And Deimos has an angular distance of 1467 degrees from its starting place. And if we subtract off integers times 360, we're now at 27 degrees. For 6 Mars rotations, 148.2 hours. Deimos, 1,760.6 degrees. And now I'm going to subtract 1,800, and I find that Deimos is back across the meridian by 39.4 degrees. The meridian line has passed Deimos, would be a better way to state that. Well, what time has elapsed? Well, if I do 360 degrees plus 11.88 hours multiplied by t, this is the motion of Deimos. The motion of Mars here, 14.57 hours multiplied by t. I come up with 133.8 hours for this calculation. Let's see what the sketches reveal to us as we do this. So starting up at the top here, and I'm going to remove this extra paper. So starting at 0 hours, our observer, the observer's horizon, Deimos is on the meridian. If I go 1 rotation of Mars, 24.7 hours, then here's where Deimos started at 0 hours. Deimos is now at 293.4 degrees, around to here, and Deimos has not been on the meridian again for the point of view of an observer on Mars. Mars is rotating faster than Deimos is moving around in its orbit. So our situation is that Deimos has not been on the meridian again at this time. If we go for 49.4 hours, 2 Mars rotations, again our observer will be here. There's the horizon, there's the meridian. Deimos position. Deimos has gone around once, 360 degrees, and then an additional 226.8. You could refer back to the previous page calculation. Repeated here just roughly. So Deimos is not on the meridian, not close to the meridian. If we go for another Mars rotation at 83.1 hours, so Mars has rotated 3 full times. Here's our observer, the meridian. Mars has gone around 3 times in its rotation. And Deimos now is at 160.2 degrees relative to this 0 degree position on the meridian. Well, Deimos is not on the meridian yet, so we have to go another Mars rotation. After 4 Mars rotations, 98.8 hours, again our observer and the horizon, Deimos has gone 1173.7 degrees. If I subtract off the rotations of Deimos, 3 revolutions around the planet, then it ends up 93.7 degrees relative to this 0 degree mark. That is the meridian. Go another Mars rotation, 5 Mars rotations, and now Deimos is getting close to the meridian, but it's not quite right yet. Mars has not quite caught up with Deimos, but we're 27 degrees past our 0 degree sort of start line. If I go 6 Mars rotations, on the left here, If I go 6 Mars rotations, Deimos is now 39.4 degrees back this way. The meridian has moved past Deimos. So 6 Mars rotations too long. 148.2 hours is too long. So again, here's our calculation. 133.8 hours. That was the time on the previous page. The angle Mars has moved through, 1950 degrees. If I subtract off 1800, that's 5 times 360, 5 Mars rotations. So we're 150 degrees past that. So if I call this 0 degrees up the top of my Mars sketch here, and we've moved 150 degrees to the position where this observer is drawn. What about Deimos? Deimos, for 133.8 hours, the calculation says Deimos has traveled 1590 degrees around its orbit. Again, subtract off 1440 degrees, and that is 4 times 360. Deimos has made 4 revolutions of the planet plus 150 degrees. So Deimos was out here, and it's now moved 150 degrees, and we have Deimos on the meridian again. So in fact, this 133.8 hours is a legitimate number. This is the time that it takes Deimos to get back onto the meridian. Now, this is not a calculation regarding phases of the moons. That would be, full moon or new moon or quarter moon. This is being on the meridian again, so it's not regarding phases that you're perhaps used to talking about, but being on the meridian for the local observer, not caring where the sun is in the sky, but for the local observer, what's happening. And there's your calculations illustrated with the sketches. If you want to see some more of these videos, you can go to my website where they're indexed at physics.gpclements.com and astronomy.gpclements.com. This video is going to be in both of those locations, but it's totally free, no registration. You don't put in your email address or anything. You won't get any email from me. But annotated lists of YouTube videos, there's over 500. I hope you find some are useful. So keep reading, keep doing sample calculations on your own.